Okay, so this is Chapter 5, Covalent Compounds and Molecular Geometry. I already wrote out some notes, and I'll scroll down as we keep going. So this is, remember the experiment we did the other week with electrolytes and non-electrolytes? We basically had water in a cup, one with sodium chloride in the water, and the other cup had water with sugar, C6H12O6. And then you had a battery with some thumbtacks at the bottom, and when you put the battery onto the thumbtack, one produced bubbles and one did not produce bubbles. You learned that the reason that the water and sodium chloride produce bubbles is because sodium chloride is an ionic compound. So what ends up happening is you have electrons available in solution to carry or complete the circuit in the water and cause the electrolysis of water. So remember that an ionic compound is a metal bound to a nonmetal. But what about the sugar? Clearly there are bonds in the sugar because the molecule is put together as C6H12O6. What holds that together if it's not an ionic bond? When a nonmetal is bound to a nonmetal, it's a covalent bond. If you look at the word covalent, more than one, or sharing, and then valent, outer shell. So the outer shell electrons are being shared in covalent bonding. Your first thing that we're going to look at is chlorine. And chlorine exists naturally. It actually exists as Cl2. Let's look at the electrons and how chlorine shares its electrons. So I have here in pink a picture of chlorine with its 7 electrons around each one. 7 because it's in group 7A, the halogens, but it wants 8. So a way that it can perceive or fulfill that having 8 electrons around it, that's also called the octet rule, is by sharing that single electron from each chlorine. You can see here, drawing arrows down. So then the chlorine shares that electron, and the chlorine on the right perceives that it has 8, and the chlorine on the left perceives that it also has 8 electrons, and that satisfies the octet rule. And one of the really interesting things is there are several compounds that exist in nature bound to themselves as molecules. So whenever you see hydrogen, nitrogen, oxygen, or any of the halogens, they do not exist as just H or just N or just O. They exist bound to themselves. So they actually exist as H2, N2, O2, F2, Cl2, Br2, and I2. And I like to remember these by saying H, no, halogens. And if you look at the periodic table, you can go across H, no, halogens. Another way that people like to remember this is with the word Brinkelhoff, Brinklhof, and then a 2 next to all of them because they exist as homonuclear diatomic Brinkelhoff. But I like H, no, halogens. So let's start to look at Lewis structures of covalent compounds. Let's look at methane, CH4. When you draw a Lewis structure, what you want to do is start with the element or atom that has the most unbound electrons, the most free spaces for electrons to take up. So if you look at carbon, carbon has 4 electrons, and in order to satisfy the octet rule, it would need 4 more, so it has 4 electrons. And then you have 4 hydrogens. And each of those hydrogens has 1 single electron. So the way that those are going to covalently come together is that each of these hydrogens are going to share its electron with carbon, and carbon is going to share those 4 electrons between each hydrogen, and they're all going to be happy and perceive that they have an octet, and so 8 electrons. So the way that looks is, here's carbon with his 4 electrons, and I will put hydrogens, electrons, and the H's in purple so you can see those. and there are the 8 electrons. So hydrogen is happy because it thinks it has 2. That's the quote-unquote octet rule for hydrogen. It can only have 2. And carbon has its 8. So then it looks like this. Hydrogen is the only one that does not need 8 electrons to feel satisfied. Everybody else needs 8. Helium only has 2 electrons and it's a noble gas, so it doesn't play with others. Remember, it's high and mighty and doesn't want to be around anybody. Okay. So keep in mind, covalent compounds do not contain metals. So if you see a metal in the compound, that should automatically disqualify it from a covalent compound. Now let's practice drawing some Lewis structures. We'll look at example 5.1. And it says, what is the Lewis structure for NCl3? Nitrogen is in group 5 and has 5 valence electrons. One's 8, remember? Chlorine has 7, and there's 3 of them. All right, so remember the one in the middle is going to be the one with the most spaces to put electrons. So this one has 3 spaces and all the others only have 1. So that would mean nitrogen goes in the middle. So here's nitrogen. I'm going to put it in the middle with pink electrons. 1, 2, 3, 4. There's its 5. And then I'm going to do chlorine. I'm going to draw chlorine in purple. And its electrons in purple too. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that is what NCl3 looks like. You can also draw it this way. The lone pairs and the electrons around here. So that is what NCl3 looks like. What about water? What does it look like? Water has oxygen. Oxygen has 6 electrons. 4, 5, 6. We have hydrogen, 2 of them with its just 1 single electron. The one with the most available spots is the oxygen, so it's going to be the central element or atom. 2, 3, 4, 5, 6, and we'll do hydrogen with its 1 electron in pink. So then water ends up looking like this. Or with 2 lone pairs here. Later on, you'll see that those 2 lone pairs actually play into a lot of very important characteristics of water and polarity, but that's for next class. So this seems pretty easy. Probably looking at this like I could probably do some Lewis structures, but let's do a couple more complicated Lewis structures. And let's look at oxygen and nitrogen, some of our homonuclear diatomics. Oxygen exists naturally as O2. And you just saw that oxygen has 6 electrons around it. So what you automatically might think is, oh, well, I'll just shove these 2 together and that'll be how they bind. That's their Lewis structure. So let's just pretend like we do that. We'll put the left oxygen in pink, his electrons in pink. We'll do the other ones in purple. But even if you were to look at this, this still only looks like it has 7. And this one too only looks like it has 7. So that does not fulfill the octet rule. So it's not 8. That's not how it comes together. What it actually does is it shares more than one pair of electrons. So here's oxygen. Here, we'll do the same thing. The one on the left and right in pink, and then the one on the right in purple. So here's his electrons now. 1, 2, 3, 4, 5, 6. And then this one, 1, 2, 3, 4, 5, 6. And what ends up happening is this guy thinks it has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then this guy also thinks it has 8 electrons. So what is this? If we rewrite it this way, oxygen has 2 non-bonding pairs of electrons on each one and a double bond right here. So we've now seen that things can have single bonds, like you saw up there with water and methane. Oxygen has double bonds. And then let's also look at one that's even more complicated, nitrogen. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's its 5 electrons on each one. So how do we organize this so that it works? And actually, all of these electrons on this one, all of these electrons on this one are going to end up sharing this way. I'm going to move these 3 electrons to the middle. 1, 2, 3. So there's its 5. I'm going to move those 3 from this one to the middle too. 1, 2, 3, and leave the lone pair at the top. So each side, you can see now, thinks it has 8 electrons. This is a triple bond with 2 non-bonding electrons on the top. That triple bond is a pretty big deal. Triple bond is very hard to break. It's very, very stable. It requires a lot of energy to break. And that's partially why nitrogen is so stable in our atmosphere. Remember we talked about during the flame test how it's a very good thing that nitrogen is inert, otherwise there would be small combustions happening around us all the time. But nitrogen is there in the greatest quantity compared to the other gases, and part of its stability is due to the triple bond in between the 2 nitrogen atoms. Let's look at a couple more Lewis structure examples, and then we'll talk about naming, and that will be it for this part of the chapter. We'll do a pretty solid review of this half and a few more things next week. So let's look at example 5.2. But first, let me throw in some questions for you. 1. Please give me the chemical formula for this compound. And then 2. Let me think. Something for you guys to do. I'll do another question in a minute. So I need the chemical formula for this compound. And now example 5.2. CH2O. So where do we start? We're drawing a Lewis structure. Let's look at how many electrons each one has around it. Carbon group 4, 1, 2, 3, 4. 2 hydrogens, each with 1 electron. And 1 oxygen with 6 electrons. 2, 3, 4, 5, 6. The central atom is the one that has the most spots to put electrons. So the most unpaired electrons. So this one has 4 unpaired electrons. This one has 2 unpaired electrons. And these each have 1. So carbon goes in the middle. Let's do our carbon with its 4 electrons. 2, 3, 4. And then you simply put the other ones around it right now. So let's put the hydrogen in red with its electron, the 2 of them. And then oxygen in purple. One, 2. There's 4. There's 6. But actually, one of these is going to move up to here. So let me erase those. Well, we don't have to erase those quite yet. Okay. Hold on just a second. Let me erase this. I'm trying to think of a good way to explain this before we move on. So each hydrogen has 2 electrons. They're all set. The carbon, though, still only has, it's still missing 1 up here. You see that? And then the oxygen, I drew that wrong. Hold on a second. To put oxygens over here. Oxygen is just hanging out over here, like this. Hold on, I'm drawing something wrong. 1, 2, 3, 4, 5, 6, 7. So what's going to end up happening is this electron from the carbon is going to come here, and this electron from the oxygen is going to come here to make a double bond. So you'll have carbon, 1, 2, oops, sorry. I get in the habit of drawing the carbons that way. 1, 2, 3, 4. That's from the carbon. And then we have hydrogen down here, each giving 1 electron. And then we'll have oxygen with its 6 electrons. 1, 2, 3, 4, 5, 6. If we redraw it, there you go. So just be careful when you're drawing the unpaired electrons, kind of like I lost count up there. Just be careful when you're drawing them and go back and count to make sure. If something doesn't look right, or if you end up with an unpaired electron somehow, the chances are you're probably going to have something with a double bond. So let's look at one more, and we'll do plenty of practice with this when I get back. I might even leave a worksheet for you guys that'll be optional to do. HCN. So we have H with its 1 electron, C with its 4, carbon with its 4 electrons, and then nitrogen with its 5 electrons. 1, 2, 3, 4, 5. All right, so as always, the one with the most spots is the central atom. So in this case, it's once again carbon. So let's draw carbon with its 4 electrons around for now. We'll draw the hydrogen bound to it, and then the nitrogen. There's its 5 electrons. And see, there's the case again where you have unpaired electrons hanging out. So in this case, you have this unpaired electron and this one, and then these 2 unpaired electrons. So remember, they'll go in here, and if they can make it feel like 8, they will, to make a triple bond. So then you end up getting carbon will have the one over here that's going to be bound to the hydrogen, and then here's 1, 2, 3. So there's carbon's 4. Here's hydrogen, and then nitrogen. Remember, nitrogen has 5. 1, 2, 3, 4, 5. And if we want to redraw this, looks that way. Okay. So we've done a fair amount of looking at Lewis structures, and we've talked about just every time we look at compounds, we aren't naming them so far. So let's work on naming. It was pretty easy to name ionic compounds, but the way we do covalent compounds is very much based on using prefixes. You're going to have to memorize all of the prefixes. Going back up, yep, there's your first question. I'm going to put another question here in just a second after we learn some prefixes. So here's your prefixes. Your book only goes through hexa. I'm going to have you guys go up to deca, which is 10. So mono is 1, di is 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10. So you will have to memorize it. Don't be surprised if you guys get a quiz. So how would we name this? What would we do? Let's look at something like carbon monoxide. If the first element or the first atom in the compound is singular, you don't put mono. You're just not going to do it. So that's why it has carbon. And then monoxide, 1 oxygen. So the chemical formula for carbon monoxide would just be CO. So for your second question, name this compound using the rules that you just learned. And I'd like for you guys to be able to do both. Given a name, give me the formula. Given the formula, give me the name. So, example 5.3 is P2O5. So you have 2 phosphorus and then 5 oxygens. When you, the second, typically the second element in the formula, you will drop the ending and then add ide, IDE. So 2 phosphorus and 5 oxygen would be diphosphorus, pentoxide, pentaoxide. All right. How about this one? Sulfur trioxide. There's only one sulfur, and there's 3 oxygens. So SO3. Okay, what would be the name of this compound right here? Carbon. There are 4 chlorines. So carbon tetrachloride. Remember, we dropped the ending from chlorine and made it ide. How about this? How would you do sulfur dioxide? 1 sulfur, 2 oxygens. And one last one, H2S. Dihydrogen sulfide. Smells like rotten eggs. It actually is the smell of rotten eggs. Okay, we're going to stop here for your lecture. I'm going to have one more question. Let me think of one real quick. So I think you had name that one. Let's see. If you listened to this entire lecture, and you hear the last question, you'll know the answer to what is my favorite color. And it is purple, but I also really like glitter. I would do glitter purple for sure. Anyway, well, good luck on your in-class assignment. I hope you guys all finish it, and I will see you next week.